you very much.
No problem. Okay, good morning, everyone. I got your homework. Thank you for submitting it. That was great. I'm going to go over the homework, which we have only two. I hope you did practice that because that will help you on the final exam, getting a 15 free points. And then we're going to start reviewing chapter 9 and 10 and 11. And we'll see where we're going to get. In the meantime, you have any questions or concerns, please make sure you ask or stop me, because that's very important. I want you guys to be well prepared for final exam so you can all score great. And so you can be happy, and I will be happy. Now, the first problem, we have the given information was a dry bulb temperature of 30 degrees Celsius and a relative humidity of 80%. Well, obviously that is hot and very humid. So let's say if here is the 30 degrees Celsius, then we just draw the line going to hit 80% relative humidity. The green line here, curves are the relative humidity. So that would be our point A. Now to find omega, we go to the right, perpendicular to omega axis or parallel to dry bulb temperature axis. And we find omega for point A. In this case, the omega would be 0.0217 kilogram of H2O divided by kilogram of dry air. Please make sure when you're taking a test, make sure you put the units next to the numbers. Just don't let them hang in there. So that's how we find omega. Again, to find the enthalpy, we're just going to draw a perpendicular line to the enthalpy axis from point A, and that will determine the enthalpy at point A. In this case, this would be 85.5 kilojoule per kilogram. I was looking at your homework, and I was happy to see that most of you got these numbers, and that was pretty good, seeing that. Now the dew point temperature, again, we're going to continue that line that we went to the omega in the opposite direction until we hit the 100% saturated relative humidity, and this will determine the dew point for dew point temperature for point A, and that is equal to 26.2 degrees Celsius. Of course, you don't have to be that accurate. 26 is fine, 25.5 is fine, 27 is fine. As long as you're pretty close, that would be fine. Now we have the wet bulb temperature. Again, the blue line represents the wet bulb temperature, and my point is located between these two lines. Reading the value of the upper and the lower, I can, since that my point is closer to the lower one, I can just guess that this is around 27 degrees Celsius. So the wet bulb temperature is 27 degrees Celsius. And finally, the volume, similar situation, those maroon lines represent the volume. And my point is between two volumes, and I can just guesstimate the closest to it. And the volume for point A becomes 0.88 meter cubic per kilogram. So given the two parameters, we run an Raman cycle, and we found all other 5 parameters. Again, when you're taking the exam, make sure you have a ruler and a pencil. That will help you, because I don't want you to ruin your textbook. Just use a pencil, draw these lines, find your points, and having a ruler will help you to read the values much easier than just trying to eyeball it, because sometimes you just miss it. Do you have any questions or any concerns about this?
Professor, sorry, please, what's the unit for the WA? I can't really see.
The omega?
Oh yeah, the omega, yeah. What are
Okay.
Yeah.
What is your question?
What are the units for omega? I can't really see.
Oh, I'm sorry.
Thank you.
It's a kilogram of H2O or kilogram of vapor, whichever you like, divided by kilogram of dry air. That answer your question?
Yes, thank you.
Oh, no problem, my pleasure. Any other questions? Now, how many of you basically got these numbers or something close to it?
Got most of them.
I did.
Same here.
All right, that's fantastic, because I look at your homework and I saw a lot of people did that, and that's a very good news. All right, the next problem, it's basically for English unit. So to get for English unit, basically we have to go to the psychometric chart for English unit system. In this case, we have a dry bulb temperature of 90 degrees Fahrenheit. And this time, it's a little different. The two parameters that are given are different. So I did that intentionally so you can be prepared. As long as you have 2 points that they cross each other, that's all that matters. All right. Now, temperature, the dry bulb temperature is 90 degrees Fahrenheit, and the wet bulb temperature is 85 degrees Fahrenheit. So obviously we are in a very hot spot, summertime. So what we do, we just come down and we look at the dry bulb temperature of 90 degrees. Now, I look into this, wet bulb temperature line to find the 85. And what I'll do is just draw the line. Going straight up until I hit the 85 degrees wet bulb temperature. This time, this becomes my point A. Now, going to the right, parallel to dry bulb temperature axis, will give me the omega A. In this case, this would be 0.252 pound mass of H2O divided by pound mass of dry air. Now, to find the value of relative humidity, I look at all these green curve and see my point, how close to one of those are, so I can guesstimate that what would be my phi. In this case, the phi, the relative humidity, becomes 81%. It's actually 81.5, so it's 81, 82, 81.5. All of those would be a correct answer. To find the enthalpy, again, draw a perpendicular line to the enthalpy axis, and you find that to be 49.4 BTU per pound mass. Finding the dew point temperature, again, drawing a line, continuing that omega line to the left, and that will give me the dew point temperature. In this case, the dew point temperature is 83.7 degrees Fahrenheit. Again, you don't have to be that accurate. 84, 83.5, 83, even 84.5. Any one of those numbers, if you find, that would be fine and that would be correct. And finally, to find the volume, I look at my point and respect to those maroon line that I draw on the board and find the volume would be 14.4 cubic feet per pound mass. Okay, that's basically the second problem. Any questions? Adiazi, can you read that? The unit for that one?
Yes, thank you.
All right. It's basically the same thing. If it's in the English unit, it's a pound mass of vapor divided by pound mass of dry air. If it's SI unit, would be kilogram or even gram. If you want to do it in the gram, then it's different. Of course, you don't have that luxury in an English unit, but you can do it either in a gram or kilogram, whichever you prefer on an SI unit. Did anyone get any numbers close to these?
Yes.
All right, that's great. Okay, that is basically, that's the reason I gave you those two assignments. So if you have either an English unit or a SI unit, you have already practiced that. And again, my recommendation is just pick two arbitrary numbers, as long as they cross each other. You can pick dry bulb and enthalpy. You can take a wet bulb and enthalpy. You can take omega and, relative humidity, because when you draw them on, they cross each other, and then find the other values. If you practice that, you get the hang of it. So it will take you only a couple of minutes to do this in a final exam. All right, let's go back all the way back to chapter 9. Is it okay if I erase this, or you need it?
It's okay.
All right. Now, from chapter 9, there will be one question. It's either going to be diesel cycle or actual Brayton cycle. So let's just start with diesel cycle. Now, diesel cycle, we always use the PV diagram. So the first thing you do, if the problem is diesel cycle, you do the PV diagram. Do not waste your time trying to do the TS diagram also, because it's just a waste of time. So by definition of the cycle, we have process 2 and 3 at a constant pressure, and process 4 to 1 at a constant volume. And the other two, obviously, compression and expansion, would be the isentropic. So this would be the work we put in. This is the work we get out. This would be our Q in, and that is the Q out. Now, the characteristics of diesel cycle, we have what we call RV, which is compression ratio. That is maximum volume divided by minimum volume. In our case, would be V1 over V2. So this is called compression ratio. Now, because we have a compression ratio, we also have a relative volume, which is V of R is defined as relative volume at a given point. So that means at point 1, we have VR1. At point 2, we have VR2. Point 3, we have VR3. And point 4, we have VR4. There is a relationship between the compression ratio and relative volume. And that is V1 over V2 is the same as VR1 over VR2. Again, keep in mind, all of these are isentropic. Also, V3 over V4 is the same ratio of VR3 over VR4. Now, some of you made a mistake on the first exam. thinking that VR1 is equal to V1. It's not. V1 absolutely not equal to VR1. And you saw that when you look at the table, that value is totally different than the value of V1. So please keep that in mind, that's very important. The ratio are the same. That doesn't mean the value are the same. So this is very important to know. Now, here we have a little problem because V1 over V2, it's given. That's our compression ratio. V3 over VR is not the reverse of V1 over V2. So we find a way to replace that. And that's where the cutoff ratio comes to the picture. The cutoff ratio, we call it R of C, by definition, is the volume at the end of a heat addition, which is V3, divided by the volume at the beginning of heat addition, which is V2. We went through the concept of proving that V3 over V2 is also same as T3 over T2. So if you have this problem, please do not try to prove what the cutoff ratio is. The cutoff ratio is T3 over T2, simple as that. I don't want you to go around the cycle, find all the volume and plug it in order to find the cutoff ratio. So to find it, just divide T3 over T2. If you don't have a cutoff ratio, but you have T3 and you found T2, if you divide them, you get the cutoff ratio. Because of that, again, we prove that V3 over V4 is the same as cutoff ratio divided by compression ratio. Again, I don't want you to waste your time trying to prove this. When you see V3 over V4, just replace it with a cutoff ratio over compression ratio, and you're done. So you cannot solve diesel cycle problem without having the cutoff ratio. The cutoff ratio is either given or you have to find it. Now, we go through this exercise when we know that CP and CV are not constant. Once again, please make sure, read the problem very carefully. If it says CP and CV are variable or consider variable CP and CV, that means they're not constant. So we need to go to the table in order to solve a problem. So be very careful and be very conscientious of that. If the CP and CV are constant, then that's a different story. We'll show you what you need to do. Now, assuming that's the case, in order to solve a problem, at state one, we have T1 equal to whatever the number is given. We go to the table, that's A17, that's for the SI unit, and A17E is for English. Now, here we can find the value of H1. Well, in this case, we're gonna, looking at this, the Q out, let me write these things down. The Q in is equal to H3 minus H2. The Q out is equal to U4 minus U1. Why? Because they are constant volume. So we use internal energy. So if I want to find a network, for instance, I need to find the Q in and Q out. So at point 1, all I need to do is find U1. I don't need to find the H1. Now, the work of a compressor, of course, is H2 minus H1, and work of an engine would be H3 minus H4. These are the four energy values around the cycle. So if I was asked to find the work of a compressor and work of engine, then in this case, I will find H1 and H2 and H3 and H4. That's what I need. If I'm not asked to find the work of a compressor and work of engine, then that means that I need to find the Q in and Q out and find the network and move on, find the thermal efficiency. Therefore, the four values that I need around the cycle is U1, H2, H3, and U4. So at this point, I will find U1 from the table, and then I find the value of VR1. Going to state 2, I use V1 over V2 is equal to VR1 over VR2. Since I already found VR1, and this ratio was given to me from the beginning, so very simply, I will find VR2. Well, now that I have VR2, so at VR2, I go back to table A17, and this time I will find two values. H2, see that will help me the things that I need to find, and also temperature at point 2. So that's one parameter that I need. This is the second parameter. The temperature is very important because once I found that temperature, I need to use that on a state 3. Now, the state 3, two things are going to happen. I either have, if the T3 is given, then I need to find R of C. All I need to do, use this relationship T3 over T2 to find R of C. If R of C is given, I need to find the value of a temperature at point 3. So it's one of these two. You either given T3, so you find cutoff ratio, or you have the cutoff ratio, you find temperature at point 3. Now, once you find those values, then at T3, you go back to table A17, and this time you find H3 and VR3. So that is our third value that we need to find. Now we come to state 4. At state 4, we write V3 over V4 is the same as VR3 over VR4. Now, we prove that V3 over V4 is a cutoff ratio over compression ratio. So I can write this R of C over R of V. Now, I found the cutoff ratio or it was given to me as a state 3. RV, which is a compression ratio, was given to me from the beginning. So this side, it's great. VR3, I already found it as a state 3. So the only unknown would be VR4. So here, I will find the value of VR4. Once I find that, I go back to the table to find the corresponding value of U4. This is again table A17, and that's the final parameter that I need to find. So now I went around the cycle and I found all the H values and U values. So now I look at the equations that I have. I find the Q in, I find Q out, and I found the network. Now, again, to find the thermal efficiency, it's a network over Q in or 1 minus Q out over Q in. There is one more characteristics related to our diesel cycle, and that is the mean effective pressure. Now, the mean effective pressure or MEP, by definition, is the network divided by V1 minus V2. Now, the value of V1 and V2 are not given to us. The only thing we have, the ratio, but not the actual value. So very easily, using the ideal gas equations, I can write P1 V1 is equal to R T1. P1 is always given to you, T1 was given to you, R is a universal gas constant. Very quickly, we can find V1 from this relationship. Once you find that, obviously, V2 would be basically V1 over R of V. Whatever that compression ratio is, that would be, you divide this by that compression ratio, you find V2. Now you have both of these. You already found the network to this relation right here, which is Q in minus Q out. So you can find the value of MEP. That's basically what we have on a diesel cycle. Please keep in mind that in a diesel cycle, we look at volume ratio, and relative volume. When you go to the table, do not waste your time finding PR1 and PR2. Why? Because you don't need it. We have no use for it. Don't try to find all the pressure around the cycle because we don't need it. They have no use for it. Everything that relates to the diesel cycle, it's all volume and relative volumes and cutoff ratio and compression ratio. Any questions?
Professor, I have one question.
Sure.
For this diesel cycle, will the compression ratio always be given?
Yeah,
Okay.
that is not something that you need to figure it out. Any diesel cycle problem the first thing they're going to tell you when we do the compression ratio. So you always have that. The cutoff ratio is sometimes given. If it's given, as I said, you need to find temperature at 0.3 because you need it to find H3 and VR3. If it's not given, then the T3 given to you in a problem. It's one of each. There is no way that they leave two unknowns. They don't give you the TR3, they don't give you the cutoff ratio, and they ask you to figure it out. In that case, you have making assumptions of a cutoff ratio, which that's not for you to do, not for this class. So the compression ratio is always given. The question is whether the cutoff ratio is given to you, then you have to find T3. If it's not given to you, you need to find it. Any other question? Now, what happened if we had a diesel cycle and this time CP and CV are constant? Now, in that case, it will make our life much, much easier. We don't have to go through all these headaches of going back and forth in the text, in the table and trying to find U1 and H1, H2, H3, and U4. So, state 1, temperature is given. So now, to find the value of the state 2, we use the isentropic equation, ideal gas equation for isentropic processes. So we can write T1 or T2, T2 over T1 is the same as V1 over V2 to the power of K minus 1. And from there, we will find the value of T2. Once again, if T3 is given, we don't have to do anything. If T3 is not given, cutoff ratio is given, we will find T3. So that would be the T3 value. Now the state 4, we can write T4 over T3 is equal to V3 over V4 to the power of K minus 1. Now, here we have the compression ratio. Here we don't have these values. And what did we say? V3 over V4 is a cutoff ratio divided by compression ratio. So I can write this is equal to R of C over R of V to the power of K minus 1. From there, I can find the value of T4. Now that I have all 4 temperatures, so my Qin would be Cp times T3 minus T2. My Q naught is at constant volume, so that would be Cv times T4 minus T1. So once I find the Q in and Q out, I find the network, thermal efficiency. If I have to find the MEP, I still have to go through this exercise to find the value of V1 and V2 to plug it in to find MEP. So as you can see, rather than going through all of those headaches to find H2, H3, U1, and U4, very quickly we can solve the problem, much faster. Of course, this is not accurate. However, you cannot make an assumption if the problem tells you CP and CV are not constant, you cannot say, assuming they are. No, you cannot do that. So you need to read the problem carefully. Sometimes they play trick. Consider CP and CV at room temperature, or a cool air, or 300 degrees Kelvin. That all means that CP and CV are constant. Because as we mentioned before, CP and CV are function of temperature. As temperature varies, the value of CP and CV varies with it. Now, if we assume they're constant, if we say, assuming at 300 degrees, that means when we increase the temperature to 500 or 800, it doesn't matter what we do with it, CP and CV value stays the same. So keep that in mind, read the problem slowly and very carefully. That is to your benefit. You can make it much easier if it goes that route. Any questions? Okay. That's basically all we need to do to know about diesel cycle. Remember these two equations for diesel cycle. Again, we deal with the volume ratio. Again, volume ratio, which is, in this case, we replaced it by that. You don't see any pressure anywhere, or pressure ratio, or relative pressure, none of those. So now we will look at the now the next one would be actual Brayton cycle. Actual Brayton cycle has a TS diagram. There are two isentropic processes and two constant pressure processes. 2 and 3 is constant pressure, 1 and 4 is constant pressure. In the case of actual, this becomes 4S, and this would be 4A, the actual value. This 0.2 would become 2S, and that would be 2A, the actual value. We're still going to have the Q in, Q out. This is the work of a turbine, and that would be work of a compressor. So that's the TS diagram. If this is given to you, you do this TS diagram, you get 10 points. And this is on your textbook, you can just copy it, you don't have to memorize it. Now, let's talk about characteristics of Brayton cycle. Brayton cycle, we have pressure ratio. opposite of diesel cycle that we have a compression ratio, now we have pressure ratio. By definition, it's a maximum pressure divided by minimum pressure. In our case, would be P2 over P1. Of course, keep in mind, we have no use for the PV diagram in this case, because TS diagram is the one that's helping us out. We don't have to write the PV diagram. So that would be P2 over P1. It's the maximum pressure divided by minimum pressure. And we generally show that as R of P. Now we also have relative pressure. Which we show by that is relative pressure at a given point. And we show that as P of R. So we have PR1, PR2, PR3, and PR4. At any of those points, we have a relative pressure. Like diesel cycle, there is a relationship between pressure ratio and relative pressure. So PR2, I'm sorry, P2 over P1 is the same as PR2 over PR1. Once again, P2 is not the same as PR2. Their ratio are the same, but their value are not the same. Similarly, we have P4 over P3 is same as PR4 over PR3. Now, P2 over P1, we call it R of P. So this ratio is equal to R of P. The good thing about the Brayton cycle, PR4 over PR3 is the reverse of a compression ratio. So this, you can write equal to 1 over R of P. You cannot do that on a diesel cycle, but here, that pressure ratio of P4 over P3 equal to PR4 over PR3 is the same as 1 over R of P. Now, since we don't have any constant volume, so all we need to do, go around the cycle and find just the H value. That's it. So in our case, the Q in would be H3 minus H2. The Q out would be H4 minus H1. Work of a compressor would be H2 minus H1. And work of a turbine would be H3 minus H4. However, since this is an actual cycle, we need to put the actual value. So in this case, that would be H2A minus H1. This would be H4A. Again, this is H4A, and this is H2A. Now, how do we find these actual values? Well, let me do this. Network never changes. Q in minus Q out, or work of a turbine minus work of a compressor, and thermal efficiency is equal to network divided by Q in, or 1 minus Q out over Q in. these two never changes, regardless of chapters 9 or 10. However you find the Q in and Q out, the network is the difference between them, or the difference between work of a turbine or work of a compressor. Thermal efficiency, it's always remained the same. Now, there is one more thing about Brayton cycle, and that is what we call back work ratio, which is the ratio of a work of a compressor divided by work of a turbine. Now we need this ratio to realize how much of the power that we generate into turbine it will go to basically run our compressor. If this ratio is very large, that means our system is not efficient. If this ratio is lower, that means we have a very good system. So that's the final characteristics of diesel cycle. To solve a problem, I'm sorry, I apologize, Brayton cycle. To solve a problem at state 1, once again, at T1, we go to table A17, and this time we find H1 and PR1. We come to state 2, where at PR2 over PR1 is the same as P2 over P1. This is of R of P. PR1 we found it from this state, so our unknown would be PR2. Once we find that, at PR2, we go back to table A17. This time we find H2 and T2. Now, since we have actual cycle, this point that we find is actually T2S, because you cannot find the actual value through this process. We need to take one more step, and that is efficiency of a compressor is work of a compressor isentropically divided by work of a compressor actual. That means H2S minus H1 divided by H2A minus H1. We already know H2S, we already have the H1, and the efficiency of the compressor is given, so we can find the value of H2A. This is the value that we want to use, not H2S value. Now we go to state 3. Again, at T3, we go to table and we find H3 and PR3. Oops. Now for state 4, we're at PR4 over PR3 is equal to 1 over R of P. So this way we can find PR4. Now that we have this value at PR4, we go to table, and this time we find the value of H4S. Once we find that, then we need to use the efficiency of a turbine is equal to work of a turbine actual divided by work of a turbine isentropically. That means H3 minus H4A divided by H3 minus H4S. Efficiency of a turbine is given. H3, I found it at a state 3. H4S, I just found it on the table. The only unknown would be H4A. And that's how we find the value of H4A. Once you have those values, you can use this equation, find the Q in, Q out. If they ask you to find a backward ratio and you find work of a turbine and work of a compressor, the difference between them will give you the network. Of course, in order to find the thermal efficiency, you still need Q in. But in this case, you don't need to find the Q out because you already found your network, you found the Q in, and that will give you the thermal efficiency. Again, we go through this hectic practice because CP and CV are not constant. Do you have any questions? Okay. Now, what happens if CP and CV are constant? If CP and CV are constant, it makes our life much easier. Here, Q in would be CP times, T3 minus T2A. Q out would be CP times T4A minus T1. Work of a compressor would be CP times T2A minus T1. And work of a turbine, again, CP times T3 minus T4A. Once you find those, network and thermal efficiency remain the same, backward ratio remain the same. Now, it makes much more easier to solve a problem when we have CP and CV constant. Now, if CP and CV are constant, if that's the case, T1 is given. You don't have to do anything. T3 also is given. So all we need to worry about finding T2A and T4A. So now we're using the ideal gas equation for isentropic processes. So T2A over T1, I'm sorry, T2S over T1 is equal to P2 over P1, which this is of R of P. From there, we will find the value of T2S, but that's not what we want. Now, the efficiency of a compressor is CP times T2S minus T1 divided by CP times T2A minus T1. The CP cancel each other out, so we don't even have to write it. So looking at this side, efficiency of a compressor is given. T2S, I found it. Oops. I had a mistake and nobody caught me. That is P2 over P1 to the power of K minus 1 over K. I forgot to put that, that's the important point. So we already found the T2S from the isentropic, ideal gas equation for isentropic processes, and the only unknown would be T2A. That's how we find T2A value. To find the T4 value, we do the same thing. T4S over T3 is P4 over P3 to the power of K minus 1 over K. And we said P4 over P3 would be 1 over R of P to the power of K minus 1 over K. From that relationship, we will find the value of P4S. Now, using the equation for efficiency of a turbine, we can write, I'm not going to write the CP anymore. That would be T3 minus T4A divided by T3 minus T4S. Again, we have the value of T3. We just found T4S. The only unknown is T4A. So from there, we find T4A value. So two temperatures were given to you. Very quickly, you find the other two temperatures. Once you have it, you go back, you find Q in, Q out, work of a compressor, work of a turbine, whatever they ask you to find, and then the rest becomes piece of cake. As you can see, this is extremely faster and very easy to do it that way. So please pay attention. Again, I brought this to your attention last time. Sometimes the problem doesn't tell you whether CP and CV are constant or not. They just don't say anything. That's the time you should be smart. So what you do to make it easier for yourself, you say, assuming CP and CV are constant. If the problem doesn't say anything at all, then you can make that assumption and solve a problem this way, rather than doing it the hard way. Be very careful. One other thing that I want you to know, there's equation 9.17 that shows you how to find the thermal efficiency by having the R of P. You can only do that under two conditions. One, you can use this equation when CP and CV are constant. Two, there are no compressor efficiency and thermal efficiency involved. That means it has to be 100% isentropic. There is no efficiency given, CP and CV are constant, then you can use this equation 9.17 on your textbook. Otherwise, you cannot use that. And some of you did that on when we had a test on chapter 9, because you didn't pay attention that this was an actual cycle. So every time you have efficiencies, you cannot use this equation. If CP and CV are not constant, and this is not an actual, it's isentropic, Brayton cycle, you still cannot use this equation because CP and CV are not constant. So little tiny small details like that will help you to make the right decisions. So please, again, you have plenty of time. If you spend 30 seconds and read the problem, slowly find out exactly what you have, what you need to find, then start thinking about what would be your approach. But if you read it very quickly because you're so anxious, because you think you're running out of time, you are making mistakes, then you get into trouble, then you waste more time, and at the end, the result is not to your advantage. Any questions?
Professor, so for
Sure.
both the SI and English system, K is always 0.4?
Yeah, because if you, the value of K is a CP divided by CV. That's the value of K. So whether it's English or whatever unit is, because this ratio determines the value of K and has no units, it will remain 1.4 for air. Not for everything, all gases, just for air. Now, sometimes the problem will tell you what would be the value of K. They say assume K is 1.5 or 1.3 or 1.3.5. In that case, you have to use the value that is given to you. But if it's not given, whether it's an English unit or SI unit, the value of K is 1.4. That was a very good question. Any other question? So you're telling me now you're expert in chapter 9. Happy to hear that. So again, in chapter 9, you're either going to have with a diesel cycle to solve a problem or an actual Brayton cycle. Please do not forget to show the efficiencies on your TS diagram. If you don't show that, even all the work you did is okay, you lose half of the point. If this has 10 points, you get only 5 because you need to show the efficiencies. So that's very important. Keep in mind, there are reasons we're doing the TS or PV diagram. This is our guide to solve the problem. Our solution has to match the TS diagram. If you don't show those efficiencies, yet you go through the exercise of finding, these values, the compressor, the T2A and T4A, that is wrong. That's not the sign of a good engineer. Because you're showing a solution that is different of what you're showing here. We have a few people who made that mistake on your project. I told you that PowerPoint presentation should be the highlights of your report. But some of you spend the time working on a PowerPoint presentation without having a report in front of you. And that was one of my comments, that your PowerPoint presentation is different than what you have in your report. You cannot put something in a PowerPoint presentation that is not in the report because it's going to confuse your client. In the future, when you are working on a project and you're writing a report and the client will ask you to come in and make a presentation, they want to know, because they have a report in front of them. They want to know when your PowerPoint presentation matches what you have done and what you have written in the report. You can add more picture to that or add more graphic design to that, which you didn't put it, on your actual report. So again, this is a similar thing. The solution of your problem has to match your TS diagram, has to match your PV diagram. Do not change the numbering that somebody did in the last test, because those numbering are not matching what you're reading the problem. When the problem says the air enters the compressor at so and so, that's your source, that's your initial point, that's point 1. You cannot call that point 4 because you're confusing everyone else, including yourself. So just use the numbering system that we use all the time. Don't try to be different, because you're just going to lose it. There's no need for that. Anyway, any questions on chapter 9? Any question at all? Any part that you want me to explain one more time?
Yes,
Yeah.
Professor. You said on the final, we may have to like figure out whether CP and CV are constant depending on what they say for a diesel cycle.
No, you misunderstood me. I said read the problem carefully.
Yeah.
You may find a problem that does not say anything at all about whether CP and CV are constant or not. If and only if that's the case, then what you're supposed to do? Engineers are supposed to find the easy way out. You have choices. You can go to the table, or you can make assumption that CP and CV are constant and do it easy way. That only happens if the problem doesn't say anything at all. But if the problem specifically tell you that CP and CV are not constant, you cannot go and write, well, I assume they are. You cannot do that. That was my point.
Okay.
Did I answer your question?
Yes. And
All right.
does that go for the actual Brayton cycle as well? Does that go with that?
Doesn't matter. Yeah, of course. Of course. It goes for actual Brayton cycle, isentropic Brayton cycle, goes for cycle. So
Yeah.
that's what I want you to read the problem slowly and carefully, so you understand what you have and what you need to do. So don't jump right into it and try to crunch the numbers, because you're missing the point, and that's going to cost you, a lot. And you don't want to do that. But if you read it slowly and you realize, whoops, this problem doesn't talk about CP and CV. Great, I can just write down, I'm assuming they're constant, and solve the problem that way. If the problem already told you that CP and CV are constant, then there is no need for assumption, because it's already there. And they said they're not constant, you cannot make an assumption. Don't forget that. Please do not make an assumption if the problem specifically say CP and CV are not constant. The only time you can do that when the problem doesn't talk about it at all. Nothing. There's nothing there. Then you can use that. Any other question?
Yes, Professor, I have a quick question about the equation behind you, the 9.17.
Yeah. The
So-
9.17 equation it makes it easy based on having the RFP only. You can find the thermal efficiency of a cycle in one equation. However, you have to be very careful. The number one condition to use that is CP and CV has to be constant. Then you can use this. The second condition, there will be no efficiency for compressor and turbine. You can use that. If those two conditions are not there, you cannot use equation 9.17.
Okay, thank you, Professor.
No problem. Same thing, there's equation 9.12 or 9.12 for diesel cycle. Again, if CP and CV are constant, there is no efficiencies of compressor involved. Go right ahead and use equation 9.12 if CP and CV are constant for a diesel cycle. And that equation is based on R of C and R of V, the compression ratio and cutoff ratio. You have to have both of them to use that equation. But if CP and CV are not constant, just forget it. Don't even go that route. Any other questions? All right. If you want to stick around and ask more questions in my office hour, that's fine. Otherwise, I will see you next week and we're going to go over chapter 10 review and then chapter 11 review, and hopefully you'll be ready for final. Don't forget your final is at 8 o'clock in the morning. So we're going to talk about it some more, but please don't forget that. Well, have a good day.
Thank you for the review, Professor. That was very helpful.
What was it?
I said thank you for the review on chapter 9. It was very helpful.
No, thank you. No problem. My pleasure.